Welcome to lecture 20. This is an important lecture. You can tell because in the title it says fundamental theorem. Any lecture that includes fundamental theorem of the course you're taking, you should probably pay some attention to it. You'll recall the fundamental theorem of calculus, of course, from Calc 1, though there are other really important fundamental theorems in mathematics, of arithmetic, of algebra, of statistics, of linear algebra around. Today we're going to talk about the fundamental theorem of line integrals. Right? So that's what we've been talking about in the last lecture. Line integrals are integrals over a path in space, or curve, or a line, really. So we could call them path integrals. So we're going to state the theorem, justify it. We're going to talk about its relationship to path independence, and then we can use those things to talk about, well, why do we call conservative vector fields conservative in the first place? So the fundamental theorem of line integrals is not for every line integral. It's for a more particular setup. One, it's for a line integral of a vector field, but more specifically about a conservative vector field. And so this is the only realm in which the fundamental theorem applies, is when you're doing a line integral, so you've got some path in space that you're integrating over. You have a conservative vector field defined on that space. So that means it's the gradient of some scalar valued function of two variables. So we're really combining these topics. And so this is the object that we're looking at. This little piece of notation here in the middle, it's quite neat. I like to kind of pause and say, look how far we've come in this course. Just to understand what in the world you're looking at, you need to understand quite a few things in this simple little expression. For one, C is a curve in space. So we assume it's a piecewise smooth oriented curve. Right here, that means it has a direction that we're talking about, a beginning and an end, and it's parameterized by some vector valued function. That was the first part of the course, right? We did vector valued function. So R of t, right, takes in a scalar, spits out a vector, right, a position in space. We'll write it in 2 dimensions here, but this theorem generalizes to all dimensions very easily, right? Not all the theorems we look at will do that. This one does, right? Works perfectly fine. In any dimensional space, you can have conservative vector fields in any dimensional space. This theorem applies. There's a range on t, right? T goes from A to B. There's the orientation, right? So R of A will be the beginning point of your curve. R of B will be the ending point of your curve. So that's just C. And then we've got, what is the integrand here? Oh, it's the gradient of some scalar valued function f. Again, that's what it means to be conservative. You are the gradient of some potential function. There. We did a lot of work to define what a gradient was and understand what its properties are. Now seeing it as a vector field is important. And then remember, the dot notation here is to say, okay, here, how are we adding up the values of my vector field? Well, we're moving along our curve at each point. We're going to take the value of the vector field, so the value of the gradient field in this case. We're going to dot it with the direction of that curve. There, and use the tangent vector, r prime of t. We take that dot product, we get a scalar. We integrate that scalar over the path, right? That gives us, one scalar, one number for this total integral. So much of the course is in here, right? Partial derivatives is part of gradients. Vectors from the very beginning, dot products, right? Understanding when that value is big and when it's small, or what the limits are in the dot product are, right? Integrating in general, it's kind of all buried in this one expression. Okay, but this is just a setup for a theorem. I didn't tell you what the theorem is yet, right? The theorem should tell us something about what number we get when we evaluate this thing. Now, this could easily be coaxed into a formal proof. I just want to justify what it is, in fact, but by kind of just following our nose here, we're just going to do the things that we can do with this expression. We'll see actually that we can evaluate it rather easily. So instead of giving you the punchline for what the fundamental theorem of line integrals says, let's just start with this expression and work with it and see where it leads. There's kind of only one way to go. Okay, so how are we going to evaluate this? Well, let's just say what we mean by this integral. Remember, if I have a parametrization, right, in terms of t, I can turn the line integral into a t integral. Right? That's why the parameterization is so powerful here. For all of our line integrals, we've got a formula to go from the general form here, right? the non-specific form here, to a t integral. It's a specific definite integral to compute it. So from this general form, we move into the t space, and t is going to go from a to b there. And so then what are we going to integrate on this interval? Well, we're going to take the value of our vector field, so that's the gradient of f, at the point of r of t. Right? R of t has x of t comma y of t. That gives us a vector. We dot it with the derivative of r. That's also a vector. The dot product gives us a scalar. So for each t, we get a scalar here. We can integrate that from a to b. Gets our answer. Okay, but hopefully alarm bells are going off when you look at that integrand. Gradient at r dotted with r prime. Here, if they're not, it doesn't look familiar at all. Why don't we expand this out in terms of x's and x of t and y of t. So remember the gradient, right? You have the two partial derivatives of f, right? Or more partials in higher dimensions, but for our setting, two partial derivatives of f, one with respect to x in the first component, one with respect to y in the second component, dotted with the derivative, right? That also has two components, right? The derivative of x with respect to t and the derivative of y with respect to t. So I can write out this dot product as the sum of those two things here. So I'm just changing notation. So you see the gradient here, df dx and df dy. And then you see the derivative, r prime, dx dt and dy dt. There. And then we add them together. And maybe that will ring a bell more. Df dx, dx dt plus df dy, dy dt, that's the chain rule, right? Of course. Right? So the chain rule was buried in here, even though you may not have seen it initially. And what does the chain rule say? It says, oh, what is this thing? That's the total derivative with respect to t of f, right? F depends on x and y, but x and y depend on t. That means we have the whole thing is the derivative of f of r. There, the total derivative with respect to t. That guy. Oh, we're almost done. But now look at what we have. We boiled this whole thing down, right, to a t integral of a derivative. Integral of a derivative. Right? Integral of a derivative. You know what that is. That's the fundamental theorem of calculus. Right? So the fundamental theorem of line integrals is really just boils down to the fundamental theorem of calculus. There. And so what does the fundamental theorem of calculus say? Well, it says if you take an integral, definite integral of a derivative, you just need to evaluate that function at its endpoints. So you get this expression, f of r of b, right? This function at the top endpoint, minus that function at the initial position. So look, that's the potential at the end minus the potential at the beginning. Means the line integral of a conservative vector field is the change in potential. You may have heard change in potential as a phrase somewhere in life. Well, that's exactly what a line integral of a vector field does. It just measures how much the value of the potential function is at the end of our curve. Remember, r of b is the one end of the curve, minus the beginning. Right. And that's the fundamental theorem of line integral, that if you can recognize that you've got a conservative vector field and you're doing a line integral of that vector field, you can kind of skip to the end and just find the change in potential. Right there. That's pretty profound, right? Here's the picture of what's going on in a line integral. Right? This is the statement really of it. So C is a piecewise smooth oriented curve from x1, y1 to the point x2, y2. And F is a continuous conservative vector field with potential. Well, F, I should probably spell potential correctly next time. I will fix that in these slides here. So in other words, gradient of F is big F. So we're saying if I've got a conservative vector field and I'm doing a line integral, what this says is just take the potential function at the end minus the potential function at the beginning. There's your value. I like this wording here. Notice now we've justified the fundamental theorem. We don't need to find the parameterization of our field anymore. Look at this kind of example of sorts here. So this is a conservative vector field. You can take my word for it or undo the code and look at what it is. But this is a conservative vector field. And here's my path. And if I asked you, okay, is the line integral of this vector field over this path, is that positive, negative, or zero? So I just asked you to evaluate it that way. You might if doing the tricks we did before, say, I'm not sure, right? Okay, let's see. It's negative here, and then it adds some positive values, but it turns around. This looks negative. This looks positive. This looks negative, positive, negative. I don't know, right? On balance, what happens? It could be any of those, positive, negative, or zero. However, if I'm telling you this thing's a conservative vector field, it turns out you can ignore that particular path and just worry about the endpoints. Right? We're saying the value of my line integral is just the value of the potential at the end minus the potential at the beginning. So my question about is this line integral positive, negative, or zero is really just saying, does the potential go up or down or stay the same? Well, if your brain can kind of take this vector field and see the potential, meaning here are the level curves for the potential. Right? Gradient field is perpendicular to the level curves. You can kind of see right, that at each point, the vector field is more or less orthogonal to our level curves here. Right? Remember, the vector field also points in the direction of greater levels there. So look at my curve. It starts on this level curve. Right? Don't even need to worry about what its value is. All I know is that if I follow my gradient around, I end up at a bigger one. Right? So I follow my path around, not the gradient, but if I follow the path, I end up at a bigger level than I started at. Started down here, ended up there. Okay, it's positive. I don't need to do any computation. If I just understand the objects in my picture, I realize the fundamental theorem tells me for a conservative vector field, the value of the line integral is the change in potential. This potential started on this level, it went up to this level, so I got a positive result. Pretty cool. Okay, fundamental theorem is powerful. The warning, don't apply it to vector fields that are not conservative. You will get into trouble that way here. Okay, so that's a theorem. Here's another follow-up theorem here. And I just want you to appreciate what this theorem says. The details of proving it are for another time. I don't want to take up too much of your time, but you can understand this theorem. This is a neat kind of theorem. I like these. I'm just going to give you 3 statements and say they're all equivalent. So that means if you know one of them is true about a particular vector field, then they're all true as well. So I like this. Theorems are often in the form of if A is true, then B is true. Right? An implication statement. This one's much stronger. Right? It's about a bunch of statements all being equivalent. Do you want to know those? So starting with, suppose F is a conservative vector field. So I'm going to give you some other conditions that are equivalent to being conservative. So if you know that F is conservative, then you also know that the line integral of F on any closed curve C has to be 0. Right? So I'll say a little more. What is a closed curve C? That's just simply a curve that comes back to itself. The end point and the beginning point are the same point. Right? That's all it means for a curve to be closed there. In mathematics, closed has a lot of definitions, but for a curve, it just means right that it kind of joins itself. Right there. So the beginning point and the end point are the same. Notation-wise, you might have noticed already this little circle on my integral sign. That's the symbol we use when we have a closed curve. It's just a hint to the reader to say, hey, I'm doing an integral around C, and it's sometimes called a contour. A closed contour integral. Anyway, it doesn't have any different meaning as far as mathematical operations to do. Again, it's just for a reader to say, hey, keep in mind, right? I've got a closed curve here because they're special there. So if you forget it when you're writing something, don't worry about it. You can just omit it, and it's fine. Anyway, if F is conservative, right? Supposedly this theorem says that every closed curve gets you 0 when you do a line integral. Right? That's true. I'll show that to you. And then another equivalent thing is to say that any line integral, so now not necessarily closed, right? So any line integral of our vector field depends only on the endpoints. Right? That means it's path independent. It means if I take any 2 paths between the same set of points and I integrate the vector field along it, I'm going to get the same answer every time. So all 3 of these are equivalent. If you know any one of these, you know the other 2. And let me sketch for you right? Just an idea of why these might be equivalent. This will not be a formal proof in any means. So I'll start with a conservative vector field. It's specifically y comma x, right? Y in the first component, x in the second. Should be easy enough to see. The potential is x times y. Works for this guy. So again, just one example, but it's just meant to give you an idea of why these are connected. So the first thing says, okay, if f is conservative, well, then it must be true that on every loop we get 0. And that's an obvious consequence of the fundamental theorem of line integrals here, right? If I take any path around my curve, it can be as wacky as I want. All right, but if it's closed, that means it gets back to the point it started from there. Parameterizing this would be a nightmare, but I don't need to if I know the field is conservative. I could say, oh, whatever line integral I get through this vector field right here, the potential at the end is equal to the potential at the beginning because it's the same point. And so there's no change in potential. This integral must be 0. It's kind of a fun game to play. It's just kind of see like, oh, does this quite work out, right? We've got kind of 0 over here for a perpendicular vector field. Looks like I got some negative values here, some positive values, 0, right? And check that on balance, oh, it looks like things balance out just right. Indeed, they do, and you get exactly 0 here. So if it's conservative, clearly you're going to get 0 on any loop, right? You can play this game somewhere else. Right. Still going to get 0 on that loop. Okay, but the next line says that the any line integral depends only on the endpoints. So that if I already know that f is conservative, it depends only on the endpoints. Well, from conservative to there is pretty clear, right? For the same reason. If I take a point curve here and I come over to here and I stop, all I need to measure is the change in potential between these two. So it doesn't matter if I go this way along my curve and I call that C1, or I take another path, maybe I come over here. And if I end up at the same point, I'm going to call that C2 there. Well, it's clear in both these cases that the line integral over each one is the same. It's just the potential at the endpoint over here minus the potential at the beginning point. All right, so what do we know? We say that the integral of C1 f dot dr, these are vectors, minus the integral of C2 f dot dr equals 0. In math, we have a habit of never saying two things are equivalent. We say their difference is 0. It's often easier to work with 0 on one side of an equation, and this is another case of that. So declaring that two curves have the same value is saying that, oh, the difference is 0, of course. But we know something about evaluating line integrals of vector fields, and that's that if you switch the orientation, so if C2 were to go backwards here, right? So instead of going C2 the way I have it here, if I traveled backwards along this path, all the tangent vectors would flop right to the other side. We would get the negative answer. So that's a way of saying that if I integrate around C1, f, drop the vector notations here, and then I integrate backwards on C2, and I'll just use the notations at minus C2, and so I just mean the path C2 in the opposite direction here. So if I add those two together, right, I'm going to get 0. Okay. But that just means that if I go around the loop, if I start at this point and I go this way around C1 and then I go backwards across C2, the total, which is the sum of those two, line integrals are additive in the same way. You integrate along one path and then you integrate along the other. It's the same as integrating along one after the other. You get 0. So you can see there's the connection between these two, right? That any loop right, can be viewed as two paths between the same point here, and vice versa. If you have two different paths between the same point, you can view it as a loop when you go backwards on one of them. There. So these two, I hope this picture is enough to connect them. Again, not enough to do a formal proof, but enough to connect the idea that if I go around the loop and I get 0, it's the same as that going one way between 2 points is the same as going another way between 2 points. It's this little connection there. All right, so that gives us a connection between these statements. There's one that I've omitted so far that is definitely the most difficult. Is like, okay, what if I start here? What if I start with the idea of path independence, so that every line integral of my vector field is independent of the paths? Is that enough to conclude that it's conservative? And the answer to that is yes, as well. Right? That if you start with this statement, right, that everything is path independent, or if you start here, that every loop is 0, that gives you there, then you can construct a potential function for your vector field, right? It can be done. I'm going to omit that derivation, or this video will get too long. Although I'd be happy to talk to any of you outside of class and do that. In fact, I'd be making my day by asking for that. All right, what's the last thing I want to do here is what I said is, this word conservative, we've been using it now for a couple classes, or vector field is conservative if it's the gradient of something. Where does that come from? So the following is a very classical derivation regarding mechanics. That's, the kinematics, right? Motion of bodies in space, right? Classic Newtonian mechanics here, and you may have seen this derivation before, but let's see it again in the context of our objects. Interesting on its own, also good for seeing the manipulation of these objects we have, vector fields and line integrals and what have you. So in physics, we say a force field, F, so think of force of gravity, or from electric field on a charged particle here. Right, we say a force field, right, is conservative, or it has a potential if f is the negative gradient of some function. Right? Now, people get hung up on that negative sign. I did as well. Don't. It's just a convention that makes some computations convenient. It doesn't change anything. Right? If a vector field is the gradient of a scalar function, then it's the negative gradient of some other scalar valued function. Right? Negative of the first one. So if this doesn't change which vector fields are conservative and which ones aren't. It's just a convention to say, oh, the potential, right, is the negative. The negative gradient gives you the vector field here. And this argument too is sort of an argument for that convention, but we could avoid that and we'd get almost the same. We get the same derivation, just different conventions on it. If you're still confused by that, contact me. I'll try and set it aside. It's frustrating when professors say, "No, don't worry about a sign," and you don't know why. Right? Suddenly, why in this context can I ignore a sign? In other ones, I can't. And I hear you if you're in that camp, but I need to hear what your confusion is so I can address it. Okay, so for this discussion, for the next minute or so, we'll say that a vector field is conservative. It's at the negative gradient of f. All right, so let's take the path of a particle in this vector field. Right, so some particle moves through this vector field. The force, right, pushes on it, right, here, and moves it from one place to another. Right here, so right, t is from A to B. So r is my path. Right, this particle moving in this vector field here. Right, so this force pushes it along. What happens here? So your particle has mass little m. Right. Let's compute the work that we did, or work that the force field did, in two different ways. So what does that mean? I'm going to compute a work integral, right? The vector field dot dr along C. It's a perfect setup. We've got a path in space. We've got a vector field. We've got a force field here. Force times distance gives you work here. So I'll go with the sort of the old way, right, of computing it, if you like. I've got the force of the, right, at the position along the curve dotted with the tangent vector. It's kind of direct computation of my vector field here. But then I'm going to introduce Newton, right? Newton told me that if this force field that's pushing this object, then it must be true that the force is the mass times the acceleration. Right? That's what Newton told us. And in our context here, that means the force is the mass times the second derivative of the position. Right? So vector field moving along some position r of t, right? Its second derivative must be proportional to the force there. So I just substitute in. Right? So actually, this guy is the mass times the second derivative there. And then we get the important thing is to recognize what's happening here. I've got the second derivative dotted with the first derivative. Right? So it's a derivative dotted with a vector valued function. So this is the key step. So pause this if you're understanding what was the magic that just happened. Happened here is we recognize that this double derivative dot r prime, that actually looks like the result of a product rule. Right? It's probably easier to work backwards here. Like look at this total derivative of a dot product. Right? How do derivatives of dot products work? Well, we differentiate one part and we get the second derivative dotted with the original plus, right, this guy dotted with the derivative of this guy. But since we have the same vector being dotted here, we just get two copies, so the 1/2 gets canceled. Anyway, these are equivalent. Right? Take some time with it if you don't see it. But we realize that this guy really is a total derivative of a function of t there. And this is a scalar valued function because it's a dot product right there. So it's a derivative of a scalar valued function. The fundamental theorem applies. Right? And we just say, oh, it's just this thing inside the parentheses evaluated at b minus that same thing evaluated at a. But we see r prime of b dotted with r prime of b and r prime of a dotted with r prime of a. R prime, that's velocity, right? And when we dot something with a vector with itself, we get the length of velocity squared, or length of the vector squared. In other words, what is this? I get 1/2 m times v squared, right? It's really the magnitude of the velocity squared, so that's speed here, minus 1/2 m times the speed squared here. Right? Oh, what is that change in kinetic energy? 1/2 mv squared, you've probably heard of. So that means the work done, right, is the change in kinetic energy, right? Say it was slow, and then it's moving fast, the force field must have sped it up, right, quite a bit, gave it more kinetic energy. That was one way of computing it. But remember, we said F was conservative in this setup. That means, right, it's the negative gradient of some potential. Here. And look, we can pull the negative out of here. That's no problem. But down we get the fundamental theorem of line integrals. It just says, oh, the integral of a gradient field is just a change in the potential. There. Right? So with the negative sign, using the fundamental theorem of line integral, just be careful here, we get the minus, right, the potential at b plus the potential at a. Right? So that's the loss of potential energy there. Right? So it's the difference of the potential where you ended up minus where you started from. Again, that's the reason for the negative sign here. And so that means the gain in kinetic energy is the loss in potential energy. If we take the last two slides, the end of this guy and the end of this guy, and set them equal to each other because they're both the work done here, what result do we get? We can move some signs around, and we get that the potential at A plus the kinetic energy at A is equal to the potential at B plus the kinetic energy at B. In other words, this is conservation of energy. Total energy at A is equal to total energy at B. So in a conservative vector field in a closed system like this, energy doesn't change. The energy at the beginning is the same energy you have at the end. Maybe it transferred from potential to kinetic along the way, right? Drop a ball from a height. The kinetic energy goes up, the potential energy goes down, but it's the same amount of total energy. That's why we call conservative vector fields conservative. They conserve energy, more or less. Okay, right. That's all we need. We're going to do tons of problems in class to address these things, but do look at the statement. Understand, most importantly, what context the fundamental theorem of line integral comes up in. Right? It's a line integral of a conservative vector field there. And then it's a good way to you can associate that quickly in your head that says if I go around a loop in a conservative vector field, I always get 0. Okay, see you in class.